20 yes or no questions can pin down a number between 1 and 1,000,000.
Why exactly 20? Each answer is 1 bit. 20 answers is 20 bits. But what kind of quantity is actually measured in bits? And why does a loaded coin somehow carry less of it than a fair one? Entropy is the average surprise. Consider two headlines. The sun rose this morning. Almost certain. Almost no information. A meteor hit Cleveland. Wildly unlikely. Enormous information. So information is something like surprise. Rare events carry a lot of it. Common ones carry almost none. That's our starting principle. Whatever measures information has to grow when probability shrinks, and we need to pin down the exact relationship. Now imagine two independent events, say 2 dice rolls. Their probabilities multiply. 1 in 6 times 1 in 6 gives 1 in 36. But the surprise of seeing both rolls should just add up. Surprise from the first plus surprise from the second. So we need a function that turns multiplication into addition. There is essentially one, the logarithm. Logarithms turn products into sums. That's their whole job. So the surprise of an event with probability p is the log of 1 over p. Equivalently, minus log p. The smaller p gets, the bigger the surprise. Take a fair coin, heads with probability 1/2. The surprise of either outcome is log base 2 of 2, which is exactly 1. That is where the unit comes from. 1 bit, 1 yes or no question resolved. Now bias the coin, 90% heads, 10% tails. Most flips are heads. Most flips carry almost no surprise. Only the rare tail tells us anything new. So the average surprise of this coin, averaged over many flips, must be less than 1 bit. For a 2-outcome coin with probabilities p and q, the average surprise has a name and a formula. H equals minus p log p plus q log q. This is the binary entropy. Let's plot it. On the horizontal axis, the probability p, anywhere from 0 to 1. On the vertical axis, the entropy, h, measured in bits. At p equals 0, the coin always lands tails. No surprise, ever. H is 0. As p grows, the coin becomes less predictable, and surprise grows along with it. Until p reaches 1/2. There, the coin is maximally unpredictable. H peaks at exactly 1 bit. Push p past 1/2 toward 1, and the coin becomes predictable again. Almost always heads. Entropy falls, back to 0 at p equals 1. A perfectly symmetric arch. And here is our loaded coin. At p equals 0.9, entropy is only about 0.47 bits. Less than half the information of a fair flip. The teaser's puzzle solved. 2 outcomes was just a warm-up. What if a source has many more? A die, a letter of the alphabet, a pixel value, anything with a list of probabilities. Each outcome has its own surprise, log of 1 over its probability. To get the average surprise, we weight each one by how often it actually shows up. Then we sum. That is literally the expected value of the surprise across all outcomes. Pull the minus sign out front and you arrive at the formula at the heart of information theory. H equals minus the sum over I of p sub I times log p sub I. Entropy is the average surprise. Shannon's original paper writes it with a constant k out front, but k just sets the units. Choose log base 2, set k to 1, and the answers come out in bits. That is the formula. That is all of it. So why does this formula matter beyond philosophy? 1,000,000 flips of a fair coin take 1,000,000 bits to store. 1 bit per flip, no shortcut. But 1,000,000 flips of the loaded coin, entropy 0.47, can be compressed to roughly 470,000 bits. Less than half the storage, with zero loss. This is Shannon's deepest result. Entropy is a hard flaw. No matter how clever your encoding, you cannot do better than h bits per symbol on average. It is why zip files exist. It is why JPEGs work. It is why your phone can compress your voice into something a network can carry. And the entropy you might know from physics, same formula shape, different story, both correct. This formula has a single author. Claude Shannon, working at Bell Labs in 1948. He called the paper, modestly, a mathematical theory of communication. Entropy is the average surprise,